So very good afternoon to everyone. So I will be taking the week 9 tutorial. So firstly we will be determining I will be discussing about determination of crystal structure from from a given 2 theta versus intensity data, that is from your XRD data. Okay. So we can okay. Firstly, from the XRD data, we will be having these two values like your intensity and your 2 theta value. Then we will be making this kind of table. So firstly, we will be converting your 2 theta to 2 theta, then intensity. Then we will calculate your sine theta, and then followed by subsequently sine square theta. Then the ratio will be determined of these two, sine theta and sine square theta. So let's see determination of crystal structure from 2 theta versus intensity data. So in this example, we are assuming that the 2 theta versus these values are this. Okay, and before that, there are certain points which we should ponder. Like this is a schematic pattern. In real pattern, peaks are not idealized. Delta peaks are broadened, and then there is increasing splitting of peaks with increase in your G value and theta. Alpha 1 and alpha 2 peaks get resolved in the high angle peaks, and also peaks are all not of same intensity, and then there no brackets are used around the index number. The peaks correspond to the planes in the real space. Okay, so this is for radiation from the copper K alpha, which are wavelength of 1.54 angstrom, and then the powder diffraction pattern is from your aluminum for this, and this is your indexed one. So in low angle peaks here, K alpha 1 and K alpha 2 peaks are merged. Okay, but however at your higher K alpha 1 and K alpha 2 peaks resolved in high angle peaks. This can be clearly seen. Okay, and also the peaks are not idealized delta peaks. They are broadened, and then increasing splitting of peaks with increase in G. Peaks are all not of same intensity. And further, then we will discuss how the real diffraction pattern are different from the ideal computed one. So we have seen that real and ideal diffraction pattern. In ideal patterns, the peaks are delta functions, but in the real diffraction pattern are different from the in the following ways. The first one is that your peaks are broadened. Second one is that your peak could be shifted from their ideal position. And then the third one is that the real intensity of the peak should be altered. Peaks are broadened. It could be due to the instrumental, residual, non-uniform strain, grain size, etc. broadening, and peaks could be shifted from their ideal position, and it could be due to the uniform strain, and the relative intensity of the peaks could be altered. It could be due to the texture in the sample. And what is the maximum value of a theta possible? The answer is 90 degree. So at theta is equal to 90 degree, the reflected ray is opposite in direction to the incident ray, and also beyond this angle it is as if the source and your detector position are switched. So the 2 theta maximum is around 180 degree. This one. So the X-ray source moves along this path, and your detector moves along this path. Okay. Now in this example, we will be determining crystal structure from 2 theta versus intensity data. So let us assume that we have 2 theta versus intensity plot from a diffractometer, and also to know the lattice type, we need only the position of the peaks. So here the 2 theta values are these, and then from this we calculated the theta values, and from these theta values we calculated the sine theta values and sine square theta. Then we calculate the ratio of these two, sine theta and sine square theta. So here in this case it is 3, around 4 and 8 and 11 and so on. And then we index the peaks. So the scale value whose h square plus k square plus l square should be 3. So 1 1 1 whose h square plus k square plus l square is 3. And similarly for 4, 8, 11, 12, 16 and 19. So we did all the indexing. And then this D part we will be seeing. So this D part can be calculated is depending upon the crystal structure. We know the formulas, and then from these we can calculate the D values. And also from the ratios in the column 6 we conclude that this is an FCC structure, and from that we can calculate your using lambda is equal to 2d sine theta, and then we know that lambda is 1.54 as we are using copper source, and then to your we are use for suppose we are taking 111 and then sine theta for 111 plane, and then from this we can calculate your a values. And also the error in the D spacing decreases with theta. Okay, so we should use high angle lines for lattice parameter calculation. Please note that in the sorry, note that in your mind. So let's move to the another example. So here given the positions of the Bragg peaks, we find the lattice type. So the 2 theta to 2 theta we calculated, then we calculated sine theta and sine square theta, and then we followed by the ratio of these two. So we found that the whole number ratios are coming at 3, 4, 8, 11, and 8. So we can see that this is an FCC structure. So till now anyone has any doubt, please feel free to ask me. Okay, so this is the way we can determine this. Now let's move to the another analytical method. So an analytical approach can also be used to index diffraction pattern from material with a cubic structure. So firstly let's look at the equation. So sine square theta is your lambda square by 4e square and n square plus k square plus l square. And since your lambda square by 4e square is constant for any pattern which we call A, and so we can write it in terms of your sine square theta as a square n square plus k square plus l square. Okay. So in a cubic system, the possible h square plus k square plus l square values are your 1, 2, 3, 4, 5, 6, 7, 8, even though all may not be present in every type of cubic lattice. And then further, the observed sine square theta values for all peaks in the diffraction pattern are therefore divided by the integer 1, 2, 3, 4, 5, 6 to obtain a common quotient. That is, your a value will be your sine square theta divided by your h square plus k square plus l square. Further, the common quotient is the value of a corresponding to 1. Then we can calculate the lattice parameter from the value of a by using the relationship your a is your capital A is your lambda square by 4a square, or the small a will be your lambda by 2 times root of a. So once we get the exact value of a, we can use it again to get the values of your h square plus k square plus l square for different reflections. And further, dividing the sine square theta value of the different reflections by a gives the h square plus k square plus l square values, from which HKL values of each reflection can be obtained by using standard listing. Okay. Then the aluminum XRD pattern indexed earlier is now indexed with this analytical approach. You see that the calculation of your common quotient. So firstly, the 2 theta values are given, then we calculated your sine square theta, and then we divided it, we calculated different quotient, sine square theta by 2, sine square theta by 3, 4, 5, 6, 7, and then we see that these are the minimum values. Okay, so the lowest common sine square theta value in the table is 0.0363 as highlighted. Now note that your 0.1086 also appears as a common sine square theta value in some of the columns, but this is approximately 3 times of a. So therefore we must look for the smallest value of sine square theta among the values. However, if we can realize that this value does not necessarily appear in each column of the table. Okay, so we should note that the common quotient of 0.0363 appears only in the columns of sine square theta by 3 and 4 and 8 in the previous table. So this suggests that the sequence h square plus k square plus l square value will be in the ratio of your 3, 4, 8. So we can now assume that this represents the capital A value in equation this 1 square plus k square plus l square is equal to 1. And since equation sine square theta is a h square plus k square plus l square suggests that division of the sine square theta value by capital A yields the h square plus k square plus l square value, from which the HKL value can be obtained. The calculations can be tabulated as shown in the table below. Okay, so here sine square theta, and then we divided it by a capital A value. Then h square plus k square plus l square values are these. So from here we calculate the HKL values. Okay, so since your A was 0.0363 and your small a is can be calculated by your lambda by 2 times root a, we can calculate your lattice parameter as 0.4049 nanometer. So this is your assignment. So you can I will be sharing this PPT, and you can calculate for this 2 theta time return, and then we can discuss this in the next one. Okay. So now we will calculating the lattice parameter calculation. So a very precise knowledge of the lattice parameter of material is important in your solid state investigation. So in developing satisfactory concept of bonding energy in crystalline material, crystalline solids, and determining solid solubility limits of one component in another, and also for calculating your like true densities of material and the coefficient of thermal expansion. So the magnitude of changes in the lattice parameter due to change in the solute content or temperature are so small that rather precise lattice parameter measurement must be made in order to measure these quantities with very high accuracy. So precision is reproducibility and refers to how close the measurement in a series are to each other. Accuracy, on the other hand, refers to how close a measurement is to the true value. Thus, make precise, we may make highly precise but inaccurate measurement through the use of improper methods or equipment. High accuracy can be achieved only with the equipment is well calibrated, but good precision can be achieved with any equipment provided we take proper precaution in recording and analyzing the data. Therefore, in this experiment, it is assumed that the equipment is in ideal condition and then consider equipment to obtain the best precision in the lattice parameter values. So please take in mind that your accuracy is very critical. If you want to know the lattice parameter to within 1 is to 10 to the minus 5 nanometer, you must know the peak position to within 0.02 degree at 2 theta value of 160 degree. So lattice parameter measurement is a very indirect process. For a cubic material, A is your d time root s square plus k square plus l square. Then the d spacing is measured from the Bragg's law, as lambda is 2d sin theta. So why are k alpha 1 and k alpha 2 peaks resolved at high angles? Which line to use for lattice parameter calculation? And other important points are that at higher Bragg angle, the k alpha 1 and k alpha 2 lines are resolved. Typically, we use only k alpha 1 lines for calculation of lattice parameter. The error in the calculation of the lattice parameter decreases with the increasing angle, and the high angle peak should be used for lattice parameter calculation. So instead of taking an average over all peaks or taking any of the intense low angle peaks. So now why are k alpha 1 and k alpha 2 peaks we are resolved at high angles? So your lambda is given by 2d sin theta, and then when we differentiate it, d lambda by d theta, it gives us 2d cos theta. So d theta by d lambda is 1 upon 2d cos theta. So alpha 1 and alpha 2 differ slightly in wavelength, and the difference in the diffracted angle d theta due to difference in alpha 1 and alpha 2 increases with an increasing angle of diffraction theta, plot of variation as above. Hence alpha 1 and alpha 2 peaks are resolved at your alpha at high angles. Okay. Now let us calculate the error in d spacing as a function of the angle of diffraction. So we know that d is given by lambda by sin theta, 2 sin theta. So for example, an error in theta of 1 degree leads to an error in sin theta. 1.7% at theta is 45 degree, but the error is only 0.15%. At theta is your 85 degree. Okay. So now let's calculate this. So your d is given by lambda upon 2 sin theta. So if we differentiate d with respect to theta, then we get this. So this is your error in the d spacing. Okay. It is given by your minus d theta by tan theta. This is your error in d spacing. So error in d spacing decreases with theta. So hence high angle peaks have to be used for lattice parameter calculation. Okay. So this way we can calculate. So now we will be doing an example of lattice parameter, determination of lattice parameter from 2 theta versus intensity delta. We know that the n values and then the 2 theta values are this. So we calculated the theta values and then followed by sine theta values and then sine square theta. Then we calculate the ratio, then we index them, and then we calculated the A value. So lambda is 2d sine theta. So we calculated the d in terms of A, and then we found out that A calculated from the 422 line was this. Okay. Now let's move to the another. So by this relation, your delta A by A is your delta D by D given by minus cot theta delta theta. So the term delta A by A or delta D by D is the fractional error in A or D caused by a given error in the theta. So the fractional error approaches 0 as the theta approaches 90. Okay. So if anyone has any doubt till now, we can discuss. Okay, so I will just wrap up the session. Very good afternoon to everyone. So I'm Rohit Velad and I will be taking the week 11's material characterization tutorial course. So in the last day we talked about basics of the TAM and from the TAM diffraction what can be inferred. So we were discussing about that in detail. So we discussed that phases and crystal structure types, crystal symmetry and space groups, orientation relationship between phases, determining growth direction, interface coherency, defects identification, example, twins, dislocations, ordering behavior of crystal structure and the site occupancy preferences. These are the things that can be determined from the TM diffraction. So like now the question comes, why the electrons only? So anyone would like to answer that? So the ability to resolve the tiny objects improves as the wavelength reduces. We already know that from the week 1 class, week 1 lecture. So let us consider the microscope objective. Okay, so these are the objects to be resolved. So distance between the D, and then this is the focal length of the lens. If the image plane is at a large distance, and then so then we determined that the critical angle for resolution is given by 1.22 times lambda by D. So the minimum D for which we can still resolve two objects is AC times the focal length. Okay, so D minimum is approximately F alpha AC. Then it can be written as 1.22 lambda F by D. So a good microscope objective has F by D is around 2. So with lambda around 500 nanometer, the optical microscope has a resolution of around 1 micrometer. Okay. So let's continuing on that. So the resolution of the electron microscope. So firstly, we know that it behaves as a light as well as a matter. So behaving like light, it can be as h by lambda. Matter also it can be as. So and P is E by capital E by C. And then energy can be given as hc by lambda. And for if you consider it as a matter, then energy can be written as h square by 2m lambda square. So the for the wave behaviors, images and diffraction patterns, wavelength can be termed by energies. And for the charged particle behavior, strong electron specimen interaction, then the chemical analysis is possible. Okay. So like typically electron beam current in TEM is around 0.1 to 1 microampere, which corresponds to 10 to the power 12 electrons passing through the specimen plane. So with around 100 kilo electron volt energy, these electrons travel at about 0.5 C, approximately 1.6 times 10 to the power 8. So they are separated by 0.16 centimeter. This means that there is never more than one electron in the specimen at any one time. And further, the electron diffraction and interference occur, both of which are wave phenomena and imply interaction between the different electron beams. Now, for the the fundamental constant and definition will be talk more about the electrons. So the charge is given by 1.6 times 10 to the power minus 19. One electron volt is around 1.602 times 10 to the minus 19 joule. So the rest mass is around 9.1 and 10 to the minus 31. Then the rest energy can be calculated and followed by the kinetic energy. The Planck's constant we know in 1 ampere. So the speed of light in vacuum is around this. Okay. So the de Broglie wavelength of an electron can be given as lambda is h by p, and then the relation between the electron's wavelength and its kinetic energy E. So P and E are related through the classical formula, we know that. So E is given by P square by 2m, where ME is 9.11 times 10 to the minus 31 kg, and energy can be given as h square by 2m lambda square. So h is uh, 4.14 times 10 to the minus 15 electron volt second, and we can calculate E as 1.505 eV nanometer square by lambda square. So don't confuse this with for energy of photons, which is given by 1240 eV by lambda. And for electrons, it is given by 1.505 eV nanometer square by lambda square. So let's solve an example. So we wish to observe a virus with a diameter of 20 nanometer, which is much too small to observe with an optical microscope. So calculate the voltage required to produce an electron de Broglie wavelength suitable for studying this virus with a resolution of d minimum around 2 nanometer. The f number for an electron microscope is quite large, so f by d is around 100. So try to solve this and we will discuss about. So we can solve it by d minimum is 1.22 times lambda f by d, and then we can so we find out that the lambda is around 0.0164 nanometer, and similarly we can we can calculate energy as 5.6 kilo electron volt. So that means to accelerate an electron to an energy of 5.6 kilo electron volt requires around 5.6 kilovolts. Now there is one more thing like I want to cover. So we discussed briefly about the SAED pattern in the last class. So we'll discuss about indexing SAED patterns. So firstly, we select the central spot. After selecting the central spot, we measure the distance between central spot and other nearest spots. This gives the So this is the inverse of the d spacing, 1 by d for a particular HKL. Now take the ratio of the distance measured. Compare the measured ratio with the extracted from the table 1 given below. Now start giving the indices for matching ratios as given in the table. Now cross-checking the indexing by measuring the angle between vectors joining the central spot and the other spots using the following equation. Now find the zone axis using any of the two indexed HKL, and then make sure that all the indexed HKL satisfy the zone law. Okay. So here I summarized for in table for all the details for you. So like these are the some examples, simplified examples for you. So pattern 1, pattern 2, pattern 3 and pattern 4. And then these are the, so you can all try these and you can